So good afternoon, everyone. My name is Jiaheng. Thank you so much for coming. So today I'm going to talk about identifying defects and their electronic signatures in the regrowth gallium nitride heterostructures. So yeah, I know I throw a lot of unfamiliar terms on the slide, but now I'm going to explain them one by one. So first of all, why are we interested in the regrowth gallium nitride heterostructures? Gallium nitride is a part of is a type of semiconductor that can be used in the power electronics, and actually it's really effective with the low on resistance and high breakdown voltage. It's going to be really helpful to use in our daily life. So I have some example over here. So this is a state-of-the-art silicon-based charger. This is an Apple charger, 60 watts. If I run on a MacBook Pro, you're going to be pretty familiar with this. And this one, 60 watts, is a gallium nitride charger. And it's 40% less weight, and the size of the silicon charger is less effective and lower cost of it. So that's why we're particularly interested in the gallium nitride. And the most promising structure for the electronic devices is what's called vertical structure. We have magnesium doped gallium nitride on the top. We have intentionally doped gallium nitride in the middle, and the N-type doped gallium nitride in the bottom. So I know some people are not familiar with the P-type and N-type. I'll explain a lot in the next slide. So today's my outline of the talk going to be in this part. So first of all, I can identify defects, or meaning there's a different way to make those structures and how they can affect their overall performance. I also going to study electronic signatures, which means how they actually perform in the real life, and I'm going to tell you which one is the best. So I have three different ways: ex-situ, ex-situ, and etch. Remember those names, we'll come over this just in a minute. So let's start with some like material science 101. What is a p-type and n-type semiconductors, and what is a P in conjunction? So p-type, P stands for positive. In this type of materials, there's like a more place to host an electron. We call it hole. So that's a positive. It's a p-type. And in the n-type, N stands for negative. It means that I have an extra electron in the place that can be connected into the hole. So when p-type and n-type stick together, the electron and the hole are going to attract to each other, and they're going to form something like a bridge. So it's easy for the electron to go from the higher energy to the lower energy, but hard for them to go backwards. And that's why they form a diode, which we use mostly in our daily life in all of our devices. So we have these structures made similar to the diodes. We make it in three different methods. We call the first one is called in-situ, next one is called ex-situ, and the third one is called etched. Why is it called in-situ? So we grow the whole structure without any interruptions in the chamber throughout the time. So that means there will be less contamination or like less interaction from the outside. The second one is an ex-situ. We grow to the unintentionally doped layer. We take it out for a day, so it's going to have potential contamination from the air or some other place, and we put it back to the chamber and regrow the upper layer or the magnesium doped layer. The third one, we grow to the unintentionally doped layer. We use the acid to etch down a little bit, which is a common way to treat materials in the industry, and we grow the p-type layer again on the top. So how those three different methods can affect those performance? So actually, I will tell you the answer right now. So from the IV analysis, which is the common way to define a performance of a diode, we can see that the in-situ performs the best. Look at the reverse breakdown voltage is the highest, where the ex-situ is just slightly worse than the in-situ. The etches perform really bad. It's less than 15 volts. So it's not really workable in the real life. So what caused this? Remember, it's basically the same structure, same materials. What caused the difference? So the first thing we are thinking, since there would be the contamination explosion to the air, is may change the chemical composition or what chemical elements in there. So we perform a test called secondary atom spectroscopy. It's basically use an electron to shoot at the samples and pick out all the elements up. And there's a detector going to collect them and identify their identity and the amount of them. So we can create a profile like this. So on the x-axis is the depth, which means like how deep we go into the materials. On the y-axis is the concentration of different elements. So we can see for the magnesium, the hydrogen, oxygen, and carbon, they're most likely the same, which is not very different, but they have the same chemical composition. But we do have something different at the interface. The silicon concentration change a little bit, but it usually won't have a huge effect on the performance. So we are saying, oh, they're basically made of the same thing. What can make the difference? Well, since the semiconductor is basically a crystal, we want to say maybe there's something in the crystal that makes the difference. So we study the crystallity from the XRD, the X-ray diffraction analysis. So X-ray is, so when the X-ray go into a structure of the repeating structures, they will interfere with each other and make a narrower peak. So the narrower the peak is, this means the better the crystallity is. So but surprisingly, the X sample, which perform the worst in the electronically, have the best crystallity among them all. And I was thinking, wow, the crystallity not really solve our problem. So we're thinking, oh, maybe it's because of the channel, the crystal structure, or the displacement. So we perform something called Rutherford backscattering spectroscopy. So this basically shooting the ions into the sample, and when they hit the sample, they can make kickback. By collecting all those backscattering ions, we can create the situation of the sample, or on the surface or in the channel. So I'll explain something over here. So when there are random places that are not really pushing the channel, the ion will have a higher chance to hit another atom and bounce back. When they're perfectly aligned, when they're going the channel, there's more space for the ion to fly through. So if there's a perfect channel, that means it's going to fly through without any interaction. But usually there will be the displacement, and they will interact and be bounced back. And we can quantitatively calculate the displacement. So from our calculation, it actually corresponds to our XRD data. The H sample actually have the lowest displacement atoms. But this still doesn't really explain like our results from the IV analysis. Then we are thinking, since the magic of the hole and the electrons attract each other really happen at the interface, we want to study more of the interface. And one of the intrusion or the contamination at the interface is hydrogen. So we use the ERD, the electric recoil detection analysis, to study the hydrogen profile, especially we're interested in the interface. And here we're getting something. The H sample show the only enhance of the hydrogen concentration at the interface, where the in-situ sample have the highest at the surface, corresponds to the XRD and the RBS data, followed by the in-situ and the edge. But the edge sample is the only one that has something at the interface. So we want to see how this interfacing affects the performance at all. So we study electronic signature, this cathodoluminescence, using electrons to hitting the sample and collecting the light being emitted by the sample. So we can see, so 5 keV study the interface and 10 keV study 5 keV study the surface, 10 keV study the interface. So we see at the interface, the edge sample only have the only one have the highest yellow luminescence, which usually associated with the defects at the interface. So then there's our story. Because the hydrogen present at the interface created more defects and lowered the overall performance of our sample. So in summary, we from a different way of analysis, we actually identified that the in-situ definitely have the best performance, although it have the high and it also have the lowest hydrogen concentration at the interface. So that makes it be most suitable to make those crystals. So we want to study more with the particle induced gamma ray, directly study the magnesium, which is the dopant of the p-type layer. That will give us more story of the defects and the situation. I'd like to acknowledge the Energy Institute for offering the fellowship, and the Rachel Goldman's research group, which I'm working at. Thank you all for coming. And also thank the Michigan Ion Beam Lab for helping us to set up the equipment for the RBS and the ERD analysis, as well as the Yale team who provide us all the samples. And thank you all for listening. Right, questions are welcome.
Don't be shy.
Yeah, yes.
Do you have an idea if there is a particular source for the hydrogen contamination?
Oh, yes. So remember we call this etch because we etch down by the acid, which is hydrogen rich. And it's etched down at the, what's going on here? Oh,
There you go.
here. Yeah, so the hydrogen is actually the interface between the p-type layer and unintentionally doped layer. So we are thinking it's the etching process introduced the hydrogen to the interface.
Awesome. Any further questions?
If not, very well done. Thank you.
Thank you.
Ready, Bone?
Yep.
Okay.
Thank you.
Awesome. Good
Have a
job.
good one.